Okay, so we have one talk now before lunch. So this is a talk by Matthew Thorpe, who's a member of the hub based at the University of Warwick, and he's going to be talking about neural networks from a continuum perspective.
Yeah, thank you very much, Paul. So maybe I should start with a slight disclaimer. I'm not really a neural network person. I guess this is probably going to become obvious during the talk. My background more is in sort of graph-based semi-supervised learning and optimal transport. So in this sort of second half of the talk, we'll see some ideas from, I guess, graph-based semi-supervised learning coming in. But most of this, I guess, is at least partly outside of my own sort of area of expertise. So I'm saying be gentle with me. Okay, so I'm going to try and so the talk's divided into two parts. So in the first part, I'll talk about residual neural networks, and in the last part, I'll talk a bit about sort of graph neural networks. Okay. Right, so I guess I start right from the very, very beginning. So what is a neural network? So I guess probably the simplest form of a neural network would just be essentially a class of functions going from, say, RD, which is our sort of feature vectors where they live, and putting out some other vector in RM, I guess, which is our desired output. So typically, RM is probably going to, M is probably going to be equal to 1, right? And we're looking at just like a scale of values. But in theory, right, it could be anything. Okay, so then the neural network has, the important part of the neural network has two parts. So we have this sort of affine transformation. So I don't know, do I have a, there's no pointer here. Okay, never mind. Okay, so we have an affine transformation. So this is denoted in my talk by these sort of K's and these B's. Right, so x0 is our initial sort of input, and then, okay, we apply our affine transformation, so we multiply through by the matrix K, add the vector B, and then we have some sort of nonlinear activation, okay, which is given by my sigma. We do this sort of n times, and then at the very end, we'll have one more layer, which brings us to whatever dimensionality we want. So now we apply this matrix W, okay, and add this vector C. Okay, and potentially apply another sort of nonlinear layer, and that gives us whatever we sort of wanted at the end. Okay, so one thing that I guess is sort of been observed is that in this type of architecture, when we have very many layers, then typically we suffer from what's called the vanishing or exploding gradients sort of problem, so during training. So one solution to this was to look at, instead of trying to model the increments between layers, we try and model the residual. Right, so instead of having xi, where I is the ith layer, being some function of xi minus 1, we really think of it as xi minus 1. That's going to equal to some function, and then we sort of model this function. Right, so this is, as far as I'm aware, sort of, I'd say relatively recently, sort of 2017, the sort of Haber and Rothotto paper and Wien and E, they both sort of simultaneously sort of suggested this, looking at this sort of architecture with the connection being to dynamical systems. Okay, right, so essentially the only difference is that I include these terms in red. And maybe just to point out that often this sigma is one homogeneous. So actually this 1 over n, which of course I introduced to make it nice sort of scaling, actually kind of doesn't really matter, right? If sigma is one homogeneous, right, I can absorb my n into my k and my b parameters, and so it doesn't really play any sort of role. But obviously analytically it's sort of nicer, and it allows us to sort of get the right scaling. Okay, so of course, we can rearrange this, right? And then on the sort of left-hand side, we have what looks like now like a time derivative, and on the right-hand side, we just have some function. Okay, and so now we can sort of look at, hey, can we sort of write the same problem down, but in a sort of continuum time perspective, right? So if I just let my now sort of x without the superscript n is now going to, I think this now is a sort of continuous function. Right, so I think of my xi over n, this is just going to be the value that I take at time I over n. Right, and I do the same for my parameters k, my parameters b, and right, so x is just a vector valued function, my k is a matrix valued function, and b again is a vector valued function. Okay, so very formally, right, if I take my n off to infinity, right, this is kind of what I expect, right, so my x's should become an x dot, and then my right-hand side stays more or less the same. Okay, so there's, I guess one can sort of make observations based on this sort of dynamical system. So what I'm going to say now, I guess, is sort of slightly wrong, but it kind of helps to inform, what a good architecture maybe should look like. Right, so again, I'm also not a dynamical systems person, so I'm still sort of out of my area of comfort. But what I do know about dynamical systems, right, is that you can really analyze the paths of a system using the Jacobian, essentially, of the right-hand side. Right, so in particular, if this Jacobian has positive or negative eigenvalues, right, that sort of really describes the system. Okay, so if, for example, all the eigenvalues are non-negative, right, we're going to have, I think this is called sort of stable states, right? So we're not going to have anything sort of going off to infinity, no matter where we sort of initialize, right? So this is sort of, well, maybe I just jump to here, right? So this kind of makes the learning problem potentially quite difficult. So if you imagine now all the eigenvalues are strictly negative, right, this means that we're kind of expecting everything to really contract to a single point, right? So we have like a stable point, right? And so, of course, this means wherever we start off in our state space, we go to the same point. And so, of course, this is going to make learning difficult because what we really want our learning problem to do is partition our state space. Right. On the other hand, if things start blowing up, that's also potentially sort of difficult. So based on this sort of observation, Haber and Rothotto, they produced this, several papers along with some of their co-authors suggesting various different types of architectures, all sort of based around this sort of idea that your sort of right-hand side should have eigenvalues which are kind of approximately 0. So I will say I think this is slightly wrong. So I think what I've said here is only actually correct if you have time-independent dynamical systems, right? So if my K and my B didn't depend on time, but okay, it sort of motivates, I guess, a certain class of architectures, and I guess they probably produce sort of very good results. Otherwise, I guess the papers wouldn't have been published. Okay, so just some quick notation. So my theta is going to group all my parameters. Okay, so my theta n has all my parameters for my neural network. I'm going to let x, so x, n, superscript n, this is going to now depend on, okay, an initial condition, and it's going to depend on my parameters. Okay, and this is just the output of my neural network, okay, at the nth layer. Okay, I'm going to have some training data. So I think I was already running out of sort of good subscripts to use, so I used S. Right, so I have feature vectors, XS, and then have what I think of as labels, YS, right, and I have sort of capital S of these. Okay, and so now I'm kind of interested in the variational problem. Right, so I look at how well my neural network is approximating the sort of the training data that I'm given. Right, so this first term here, right, is just summing the error of each of my training data points. And then I have these 4 terms here. And these 4 terms here are going to be my regularization, and these are just to make sure I can get like a well-posed limit in the end. Right, so I think on the next slide, right, so I have the regularization terms here. So what's kind of important is that, okay, if we want a limit, we have to have some sort of continuity. So I can't have, so for example, my Ks, they can't jump wildly between different layers. So I have to have some way of sort of having some sort of smoothness between the layers. Okay, so one way of doing this is just to look at, well, exactly, penalizing the norm of Ki with, in Ki minus 1. Okay, and then I square it, and then I sum it and normalize it in the right way. I've also added sort of a penalty on the initial value, and okay, and this, I guess, was more for technical reasons. This, I guess, is so this actually starts to look like a Sokolov norm, whereas if I had tau 1 or tau 2 equal to 0, this would actually be like more like a semi-norm. And I had very light restrictions on my actual neural network part, so I needed kind of the compactness from the regularization. Okay, and I've also included some sort of penalty on the W's and C's, which is my sort of very last layer of the neural network. Okay, so we can essentially do all the same thing now, but we can do it in the continuum setting. Right, so now my K and my B, these are functions from 0, 1, and my K is matrix valued, and my B is vector valued. Okay, and then my W and my C, they're in the same space as they were before. Okay, so now I had my sort of x, n, now I just have my x. So my x now is the solution to this, this ODE, okay, with the initial condition that x0 has to equal to x, right, and of course it depends on the choice of parameters. Right, and I have essentially the same variational problem now, right? The only difference being that I look at the endpoint or the t equals 1 solution to my ODE, and I compare that with the training data, and now I have my regularization terms. Okay, but now these, I guess, well, before my regularization, my first two depended on n. Now they're kind of set in the continuum, right? And so these are what the continuum regularization terms look like. So my finite difference, this has now been replaced with a time derivative. Other than that, they're more or less sort of exactly the same. Okay, so with this sort of regularization, we can get kind of, the theorem that, one would expect. Right, so first of all, we can say that there are minimizers to my discrete variational problem. Okay, not too surprising. We can then say that the any set of solutions is going to be compact. And we can say that any converging subsequence of my minimizers is going to converge to a minimizer of my continuum problem. So it's kind of a very basic sort of consistency type result. And we can also say that the minimums are going to converge between the two, well, from the discrete energy to the continuum setting. We get slightly more regularity than one, I guess, would sort of expect on first glance. So if you know that, okay, so if my k is minimizing my continuum problem here, right, you can see that R infinity, right, is essentially a Sobolev semi-norm in H1. Okay, and actually you get sort of, 1 degree higher, so actually you can go to H2. Again, this probably isn't surprising from an elliptic regularity point of view. And then the last is, okay, is a very, I say it's a very weak sort of convergence rate in that it almost gives you sort of, a rate of convergence going from discrete to continuum. But I think I will probably jump. Okay, so I guess this is the second part of my talk now, so maybe are there any questions at this point? Or should I just go on? Okay, so I will go on. So I guess, okay, so the second part of my talk also connects to the continuum, but now instead of resonance, we're going to look at this more in a sort of a graph-based setting. So I'll start off with graph diffusions. Okay, so diffusion in the graph setting can be written just like this. So we have our dx dt. This is now equal to the divergence. So divergence will be the graph divergence times, okay, some operator f. Okay, so f would be, okay, so in this I've written as the given function. In neural network setting, this would be the function that you would have to kind of learn. Okay, and then this function f pre-multiplies the gradient of x, okay, and this gradient again is the graph sort of gradient. Right, so a very sort of special setting for this is if we just assume that my function f is essentially 1 over the degree of my nodes. Okay, so I guess I didn't sort of explain all the notation here. So my wij's are my weights between all of my nodes. Okay, but di essentially just counting the number of edges from each point. Okay, but if we do this, right, then actually what we get is that dx dt is equal to minus this Laplacian of x of t. Right, so this essentially is, I guess, what's the heat equation, right? Okay, so it's ln tilde. This is a particular type of graph Laplacian. Right, okay, so, right, so once one writes this down, you can sort of realize that actually the heat equation corresponds to minimizing a Dirichlet energy. Okay, so this in particular tells us, what we can kind of expect if we just sort of take a limit of this equation sort of immediately, right? I mean, it's diffusion, so whatever we kind of start off with, it's going to sort of eventually become sort of constant, right? So, in particular, what we sort of expect is that if we have, so if my x, okay, so let's say my x of t is solving this equation, right? As t goes off to infinity, I'm expecting my x of t to converge to something which is independent of where I started from, and that's kind of the important part. Right, okay, so there was, so this fairly recently, so I guess just a couple of years ago, there was sort of a big class of graph neural networks proposed based on sort of diffusion equations. Right, so the idea really is to sort of model this f and then sort of, I guess train this f based on this sort of architecture. Okay, but again, so one thing this neural network didn't do particularly well was to go to sort of large data limits. So it works very well for just a few layers, but after that, performance generally starts to either plateau or even sort of decrease. Right, so right, so to try and sort of explain why this sort of happens. So intuitively, I tried to sort of reason it by sort of comparing with diffusion equations, right, and sort of saying, okay, this is really the heat equation, so this is kind of what we expect. And actually, we can really sort of analyze this a little bit more precisely using sort of random walks. So again, right, so let's introduce this random walk bt of x. So this is the random walk which starts from x, and then it's going to either stay where it is with probability 1 minus delta t, or it's going to move with probability delta t, and if it moves, it's going to move to another node proportional to its edge weight. Right, so again, these wij's are my edge weights. Right, and okay, and so it's quite straightforward, really, to show that this random walk here, let me. Right, so we take this random walk, and it starts off from these x bars in sort of k time steps. Okay, so what am I doing? Okay, right, so in every. Sorry, okay, right. So this expectation here, right, so this is the expected value of this random walk after k steps, right, and this is going to essentially solve my sort of discrete heat equation. Right, so sorry, yeah, so my x is here, right, this is more or less the, let me go back to, did I write it? Yeah, so it's more or less this dx dt is equal to minus the random walk Laplacian times x of t. Right, if you just discretize this, right, you end up with exactly this, right? So my delta t now is my time step. Right, so there's a direct connection between solving the very simple case of this graph neural network and this sort of random walk, which is eventually going to forget where it is. Right, so this random walk has a stationary distribution. So of course, as time goes off to infinity, it's going to be distributed according to its stationary distribution. Right, and the stationary distribution itself is just proportional to the degree of each node. Right, okay, so so what this kind of tells us that if we look at this sort of very simple case, right, where, okay, so admittedly we're not sort of looking at training anything, we're not sort of optimizing anything, but if we just look at the kind of the core architecture, right, we can kind of see how we can get this sort of over-smoothing phenomena. Right, so one potential solution is to start to add information back into the graph neural network as we go along. Okay, so the way we sort of proposed to do this was to add this sort of source term. So these sort of z's are going to be sort of slight modification of my sort of graph neural network proposed in sort of grand. And the only difference with it is that we have this sum over j in in of delta ij cj. So cj is going to be some sort of source information, and my in is going to be my subset of nodes where I'm going to inject this information in. So I don't have to do it across the whole graph, I just have to have a few nodes which I'm going to continually put data back in. Okay, so to get everything to kind of work well and to make a connection to random walks again, I had to choose the sort of source terms in a particular way. So in particular, I essentially had to choose the source terms to be the initial values minus some sort of constant, which was just there to make everything, I guess, to recenter everything. Okay, so I think this is the same equation as on the previous slide, right? So, okay, so but then we have the same sort of random walk point of view, but now the limit is different, right? So now if we sort of discretize our sort of graph diffusion with source, right, we get a connection to a random walk. This random walk no longer has this sort of stationary, well, okay, it's actually the same random walk, but it's a different sort of construction of it, and in particular, it won't have the same sort of deep layer sort of smoothing problem. Right, so if you look at this expectation here, this is what my sort of discrete graph neural network is converging to. And this now is almost the, you can think of this as maybe like the dual sort of random walk to the previous case. So now you think, instead of having sort of one random walk which I start off at one point and I move around my graph, and now I think of this as having sort of many random walks which I start off at each of my source terms. Right, so my sum over j and in, each element in this sum is corresponding to one random walk which starts from that particular node. What happens then is that each of these random walks kind of walk around my graph, and every time they hit a node, so say, for example, I'm interested in the ith node, here they make a contribution. Right, so I'm really looking at the frequency of how often these random walks hit the node that I'm kind of currently looking at. Right, but of course it's the same random walk, so you might say, okay, we probably have the same, it's going to have the same stationary state, so perhaps this is still going to suffer from the same sort of over-smoothing phenomena. What kind of helps us out is this sort of minus x hat. So somehow one can sort of understand this x hat as being the large data sort of, well, the large time limit of the random walk. So when we sum, so my time steps here are from, okay, they're indexed by s, so I go from s up to k. So as I take k off to infinity, right, I'm summing over all times. But this x hat is somehow like the large time, so somehow I have my all time, I subtract my large time, and then sort of very heuristically what I'm left with is my sort of short time behavior. So somehow I don't, we don't expect this to kind of behave as badly in the large in the large time limit. Okay, so I think for the rest, I'm doing quite well for time, so I think I'm probably going to finish at least a few minutes early. The rest of the, I think the next 3 slides are all sort of just numerical experiments, which essentially show that, with the right data sets and the right setup, this method works better than the previous methods. Okay, so we took 3 different data sets, Cora, Sightseer, and PubMed. And then we looked at sort of various different sort of depths, and we looked at comparing our method, which is gram plus plus, so the right 2 columns, and then with the sort of original sort of diffusion-based models. There's I guess 2 different ways of implementing these methods. I forget now exactly what the differences are, so I can't remember what the difference between the NL and the RW method is. Yeah, it's probably, I guess RW is probably random walk, so they're probably using different Laplacians, so perhaps RW is random walk, NL maybe is non-local, but I can't quite remember now. But you can kind of see that for one depth, there's not too much difference, right? I mean, they're all sort of performing, so in Cora, right, everything's sort of around 79%, not a huge sort of difference. But as the depth sort of increases, generally the gram plus plus method starts to work a lot better. In some cases, sort of fairly significantly so. So, for example, in Sightseer, you can sort of see grand is working around 65%, which actually is 6 or 7% lower than what it started off with. So really kind of adding the extra layers kind of really sort of hurt it. Whereas we go from sort of slightly worse performance, sort of around 70, 71%, but the performance sort of always increases, and we end up sort of around sort of 74%. Right, so it's so actually this architecture is really kind of motivated by some work in the low label rate regime in semi-supervised learning. So we also want to kind of test this, how well this does when you only have sort of very few sort of labels in your data set. And again, we do quite well. So yeah, okay, so I guess we're really comparing, so gram plus plus is our methods at the top, and then these, I guess, are various other sort of different types of architecture which we compared to. So again, if we look at just one label per class, right, in Cora we're getting sort of around 55% accuracy, and this is a good sort of few percent sort of above everything else. I think in general the performance doesn't, other methods sort of start to catch us up as we get sort of more labels. So if we go to around, so if you're looking at sort of around 20 labels per class, right, we're getting sort of around 83%, which is similar to grand, which is not too far away from the GCN method, right? And they're all sort of, only separated by a couple of percent. with the big difference being sort of in the sort of very low label rate regime. Okay, so I think that's probably everything in my talks. I guess here are some sort of references. And I think, yeah, thank you very much.
Okay, so we have time for a few questions.
That was a very nice talk. Thank you so much. So from the results in the first part of the talk where you were talking about these continuity limits, so does this tell you anything about maybe discretizing it differently and getting a different neural network, or using optimal control strategies for learning, or?
Yeah, okay, so very good question. So I think this sort of like has motivated different discretizations of neural networks. I mean, so there's a very good question actually last time about, are sort of deep neural networks sort of good? I guess this is all sort of done on the assumption that deep layers are good, right? So we're assuming that that's the answer to that question. But then the idea, I guess, is that if you then have like a continuum perspective, what you can look at then is different discretizations that essentially allow you to get like a deep layer, but with fewer actual layers, right? So if you think of this, so in my first part of the talk, I fixed time at time 1, but of course, right, you could rescale it and think of time as going off to infinity. But then the question then is, like, how quickly can you get to infinity? So these methods, right, I guess were this kind of the straightforward Euler discretization, right? And this is probably the most crude thing you can do. If you started using better discretizations, then perhaps you could get the same performance, but with, much fewer layers. Then you have fewer parameters to train, so then perhaps it becomes sort of a lot easier. Yeah.
My question was sort of similar, because I'm aware that many people in the room are not mathematicians, and therefore this perspective of looking through the continuum lens and linking to dynamical systems might not be the most natural way of sort of viewing neural networks. So perhaps you could just sell this viewpoint in sort of a few bullets, layman's terms. So design of better neural networks or more efficient neural networks is one thing. Is there anything else that looking through neural networks with this lens can sort of bring to the table why people should talk to mathematicians who know how to do this kind of analysis?
Yeah, so I think for me, maybe there's two things that are kind of motivating me. I mean, the first thing, I guess, is that by sort of connecting with dynamical systems, I mean, dynamical systems have been studied for, 100 years or so, right? There's so much sort of theory we can sort of build on, right? So it really means you can sort of, you don't have to reinvent anything from scratch, right? You've got all this sort of wealth of knowledge. And so I think that's quite nice to be able to sort of build your network on something, that's kind of solid. I think this is probably perhaps like an immediate sort of benefit. The other sort of thing that's kind of motivating me, I think there's really still a gap here, is that what would be nice in machine learning is to somehow close the gap between the sort of model that we use and the physics or the underlying reality. So, I mean, I can't give you an example, right, where, like, in a classification task where, a dynamical system will be reasonable, but hopefully there is kind of something there. I mean, the idea, I guess, is that you would have, really like a physical sort of model, and then once you have a physical model, I think you can start asking maybe more sort of advanced questions. So, I mean, my answer, I guess, is concerning convergence, but really the question should be sort of consistency, right? So is there some truth, and now we kind of converging to that truth, but if you have truth, right, you have to have a real model, and then, okay, then you have to connect then with sort of physics or, science.
Any other questions?
Okay, Matt, so you skated in like 2 seconds over your convergence bounds. Is that because it's so pessimistic to be worthless?
That's not far off. I mean, I think it's not quite as powerful as I perhaps would have liked. I mean, I can... it's okay. Okay, so the thing isn't working, so I can't even show it. Oh, no, it has moved now. I think it really... I don't know how much it really kind of tells you, because I think there's sort of... I looked at it again this morning. I mean, So I guess I wrote this paper, I think it was a few years ago now. I looked at it again this morning, and then actually I thought, okay, this is really, yeah, the rates isn't, it's not quite meaningless, but it's very close to being meaningless in the sense that it's kind of in terms of other parameters that you're not quite sure how they're scaling, and so, yeah, I wouldn't want to sort of sell the result as more than what it was, which is slightly more than maybe just knowing that it goes to the error goes to 0, but really only epsilon more than that. Yeah. Where epsilon is less than 1 over n. And
Okay, so I think we've come to the end of time for this session. So if we thank Matt and also Zumi again.